In this video, we'll be talking about a phenomena called motional EMF. Now, motional EMF is talking about an effect that happens when you take some conducting material and you push it through a magnetic field. What's going on here? You can understand it more straightforwardly understanding the Lorentz force law, which is to say the magnetic force on it. Now, in a lot of these effects, you can think about them either in terms of the force law or in terms of Faraday's law, which talks about EMFs being generated due to a changing magnetic flux. Now, Faraday's law is a more general law than this force law. What I mean by that is that there are effects that you'll notice with Faraday's law that you wouldn't simply by looking at the force law. However, in some cases, including this one, the force law is essentially a restatement of the effect that you have in Faraday's law. Essentially, we've secretly introduced a new set of rules that introduce some new forces into the situation, which are sometimes the same as the old force and sometimes entirely new forces. But we haven't described them in terms of this force, and we've kind of hid it all away in the package of our discussion of magnetic flux changing and inducing EMFs. I'll talk a little bit in chapter 21 about this more comprehensive picture about what's going on, but we're sort of slowly transitioning into a new field of phenomena without explicitly laying out the framework that is underlying it. So let's imagine that we took a bar and we threw it through a region of magnetic field. The case we'll be looking at is a uniform magnetic field, so that everywhere the bar is, it has the same magnetic field that is into the page, and the bar will be moving directly to the right. We'll neglect any gravitational forces in this case, and just look at any sort of magnetic and electric type effects. So, this could fictitiously be in the in deep space where we have no gravity, or we could just be talking about some scenario where we can neglect the effect of gravity. So, what would happen in this case? Now, we have some discussion based on. Let me switch over to a color here so I can draw. Based on our discussion of the forces. Now, it may not be obvious, but there's charged particles moving to the right. There are both electrons and protons inside this neutral conductor, and we're moving through a magnetic field. So if I look at, say, an electron inside of that conductor, it's going to have a magnetic force on it. So I'll do a free body diagram showing the direction of the forces on that particle. Well, if I am moving to the right and the magnetic field is into the page, then what I would find is I'd use my left hand. We use one of the right hand rules, but here, because it's a negative charge, you can use my left hand. I stick my thumb off to the right. My index finger would point into the page, because that's the direction of the magnetic field. This is the VBF, the very bad finger one, which is like the squirt gun way you hold your hand. And then your index finger would be pointing down towards the bottom of the page. So the magnetic force on this electron, which I'll write as F sub B, is downwards. Well, that would mean that this would be pushed down towards the bottom. Since it's a conductor, these electrons will move freely, so they will respond to this force by being pushed down towards the bottom. So it would have a bunch of negative charges down here at the bottom. These are attempted to be minus signs that I'm drawing. Now, since the electrons are missing from up near the top, there will be remaining positive charge. Protons who no longer have their accompanying electrons. And if you had positive charge up here and negative charge down there, you're going to have an electric force in this case. And this electric force is related to the amount of charge built up on each side. So which way would it be? Well, there would be you can kind of tell there's negative charges down here, there's positive charges up here. So an electron would be repelled from the negative, attracted to the positive. There would be an upward force in this case. So what would happen is as the charge began to move towards the bottom of the conductor, due to the presence of a magnetic force, there would be a gradually increasing electric force that would oppose the buildup of this charge. And this would increase until the point that the two were equal and opposite, until the net force on the electrons would be zero, at which point the electrons would no longer be accelerating towards the bottom, and any electrons in here that were free to move around would remain motionless. So here's what's going to happen. If I have this electric field now due to this buildup of charge, that means I have this electric force, excuse me, I'll have an electric field. And the magnitude is going to depend on the difference in charge here. And if I have an electric field, that means I have a change in voltage. I can write this in different ways. I'm going to call this delta x, where x is going to be the direction in this along here. And in fact, that the voltage difference I get is going to be the electric field times, and this will be a uniform electric field. If this is essentially going to be two parallel plates in here, is going to be A times delta x. Now, where the voltage difference from the top to the bottom would be here delta V. So if I call this length of the bar L, I can rewrite this as simply E L. Well, how big is the electric field? And we need an electric field that's big enough to cancel out the electric force. Well, what we know then is that the magnitude of the electric force, is equal to the magnitude of the magnetic force. And the electric force is QE. The magnetic force is QVB sine theta, where theta is the angle between the velocity here, which is directly to the right, and the magnetic field, which is into the page. And since into the page and to the right of the page are at 90 degrees, we have this sine of 90 degrees, which is simply 1. So this will simplify down significantly. This part just becomes 1. The charge on each side can cancel out. And what we find is that the electric field is just VB. So I'm going to plug that in as well over here. And what I find is that what I find is when I plug in for the electric field, I have VBL, where V is the speed, this lowercase v, B is the magnitude of the magnetic field, and L is this length, which is the width of the object perpendicular to the direction of velocity. If it was moving in with a component that was actually in the same direction as the magnetic field, I would have to keep this sine of theta around. So this is only in the specific case where we're now moving perpendicular to the magnetic field. We have this particular formula, but this here is our main result. I'll write that again over here. The voltage difference between the top and the bottom is VBL, which I'll write in this next page as BLV. We're just rearranging the letters a little bit. And again, that happened because we had an electric and magnetic forces that cancel each other out. Now, I can also think about this as being part of a circuit. So, and show you how this gives you the same result from Faraday's law. If I had a bar that was now on a wire frame, like a U-shaped wire frame that is being pulled over. So now we could say this is a little more realistic of a result. I could have this be a top-down perspective so that the bar was being held up, which is counterbalancing any forces due to gravity, and I was pulling it to the right. So I might have an electric and a magnetic force. And I could talk about the EMF induced in this loop because now the flux was changing. And remember, Faraday's law said that the EMF that was induced was N times the change in flux, magnetic flux specifically, over time. Now there's a couple of things I can do to simplify this. This is just one loop. There's not multiple coils on here, so N would just be 1. Also, I can now express the flux by in terms of the actual quantities here. Magnetic flux, we said, was the magnetic field times the area times cosine of this angle between that is perpendicular to this area and the angle between that direction and the magnetic field. Well, I'll choose to have, so the area is on the plane of the page, so that vector or that direction that's perpendicular to it would either come directly out of the page or into the page, and I'm free to choose which one it is. I'm going to choose this as being into the page, so that it's in the same direction as the magnetic field, in which case the angle theta is simply 0, and we have cosine of 0, which is 1. So in this case, it's just going to be the magnetic field times the area, because this is just 1. Now I want to look at the change in this over time. Because that's actually what I'm going to use down here. Well, if I could do kind of a final minus after, the magnetic field is staying the same, so I can pull that out of the difference in that delta. So it would be B delta A over delta T. And what I'm going to do is just call the current position of the bar X. The reason why is then the area of this loop here is going to be equal to X times L. And again, the L is not changing over time. It's not getting wider, but I pull it to the right. So I should say it's not getting taller. The bar is not getting longer. But the bar, when the bar moves to the right, the area gets wider. So if I look at the difference, I get B times the length times the change in X over time. Now, how many centimeters it moves over to the right every second is what we call the velocity. So delta x over delta t is simply BLV here. So I can write this as the EMF is just BLV, plugging in for the change in flux over time, which is the same formula we would have here for the voltage difference that we had before, because again, an EMF is just a voltage difference. And here, in this case, what we were saying is that this bar is going to have an electric force on it in such a way that it'll act kind of like a battery. It wants positive charge on the side and it wants negative charge on that side. So it acts like a battery with an EMF that was like BLV. So as this was pulled to the right, this would have, you can imagine as being like a battery. This would be like a circuit where there's going to be a little bit of resistance in here, this wire. Even a fairly well-conducting material will have some amount of resistance in it. And so here, this part would act like a battery, and there would be some resistance overall, and it would look like this. And what we would have is a current that would run in this circuit. And in reality, what would happen is as this current begins to run, which we now allowed to do by including this U-shaped piece of metal, let the current run around, is that we would now have a current that was in the presence of a magnetic field that would push a force back on it, which would act kind of like a drag force. So if you physically pull this over to the right, it would feel like you had a resistance on it, which is starting to get at a similar phenomena to why that dropped magnet actually slowed down. It's not this situation, but it is more similar to this. Now, I wanted to use this as an example to show that you can either talk about it in force or in Faraday's law, and you get the same result.